Now we are starting on with this is a new chapter actually. But before that, good morning, good evening, good afternoon, good night to all of you who are watching this video. So today we're going to discuss. I'm going to discuss actually. Today I'm going to focus on a new chapter, which is in particular chapter number 9. What is this chapter about? This chapter will be about what we call as autocorrelation. Let me go to this part first. Let me explore what we're supposed to have based on the chapter that we have previously in chapter number 4. Is it chapter number 4? Let me go ahead with chapter the CLRM regression or CLRM assumption. This is actually based on assumption number 6, as you can see here, right? No, sorry, assumption number 5. Blur a bit. Assumption number 5, which talks about no autocorrelation between the error terms. So here we are talking about this. We do not want to have the correlation between the error terms itself, which we negate, or we do not want the error terms are correlated with each other. So what is that all about? Let us discuss this particular chapter further. So we have so-called 4 parts of this, in particular, especially this diagnostic test started off with autocorrelation. So the first one will be, what is the nature of autocorrelation? So in other words, is that what's the nature of the issue here, right? In particular, so what's the nature of the issue? In particular, what is autocorrelation all about? What's the consequences if we have autocorrelation, and how to detect autocorrelation, right? How we could detect autocorrelation, right? Again, in this video, I will have 2 parts. One will talk about these slides first, and then soon after I will mention to you on the how we do it in eViews actually. So how to detect the third part. Again, go back here. Step number 3 here, how to detect, and then what's the remedy measure? Let's say what types of a medication that is suitable if you have the problem of autocorrelation. Let's move on to the next slides. Right, next slides here. So this is the nature of autocorrelation. I know the slides looks a bit, I mean, there's a lot of write up there in the slides, but let me go in the very, very simple meaning. We do not want autocorrelation means that the error term of one period of time is correlated with the error term of the other period of time. And this particular issue normally happens in the time series analysis, right? Means that the other, as you have to know and understand, is that we have like this. For example, you have the UT, right, which represent today. Right, tomorrow we represent that as a U team plus 1, and yesterday we represent that as a UT minus 1, or in other words, it's mu, which is error term. So this is today, this is tomorrow, and this is yesterday. This was yesterday. So what this assumption says is that this error term are not correlated with this one are not correlated with this one. Means that the past value of the error term are not supposed to have any correlation or any sort of relationship with whatever happens today. Right, here is the very good example of that. In the first equation up there, where you have labor and capital as x1, x2 for the period of 1990, 2002 in that. Right, the error term capture the factors that cannot be explained by the independent variable. This has been explained earlier on in our chapters. Chapter number 3, you can refer back to that particular chapter. In that sense, the error term also capture the shock. If 1994, there was a big fire that disrupt the production of the output, since the fire do not affect the labor and capital, the shock of 1994 will affect only the output of 1994. But this disruption of output in 1994 is not just explained by the labor and capital, thus is captured by the error term. If there is no autocorrelation, then the output disruption would only happens in 1994. If there is autocorrelation, the output shock will be carried forward to 1995, 96, and so on. This is one example. Or the other example, the other perfect example will be the ASEAN financial crisis, the AFC we call it, which happened somewhere in 1997 when all of you have not come to this world yet. Right? In 1997, 1998, Asian financial crisis, the impact was not just happens in 1997, 1998. For the years to come after 98, also the impact is still there. And one of the solutions that the Malaysian government undertake at that time was to fix the exchange rate. This was to ensure not only just fixed exchange rate, but to fully control the capital flows flowing up for the country. This is to ensure that the economy are right back on track, right? That's the idea here. But this autocorrelation means that the impact of the ASEAN financial crisis still can be felt even after 98, 99, 2000, 2001, and so on. So that can be a very good example of autocorrelation. The other perfect example of autocorrelation is what's happening right now. Right? We have the pandemic since 2019, which is why we call it coronavirus 2019 or COVID-19. The first infection was happening, detected here in Malaysia in January 2020. And now we are in the May of 2021. And the case are still there and on record high for Malaysia case. So this pandemic, surely everyone knows that the impact will not just die off in 2021, or what we have in mind saying that 2021 will be a better year after 2020 having this pandemic impact. Yes, everyone hope and pray for that, but in 2021 it seems like we still carry on. The impact of the pandemic is still there. So that's the example of autocorrelation. And we know for sure that the pandemic impact will still be there for years to come, even for next year, even for the few years to come. Things will go back. Things will not go back to as normal as what we are expecting back in 2019. Right now that everyone are more cautious. Everyone when go out will wear masks. Will have a mask protection. Online education, online class is pretty normal right now. And not only just online class, everything else goes digital. Pretty much because of the COVID-19, the acceleration of the digitalization seems to be very much on high time. And it will go on and on, I'm pretty sure. And this is what one example of what we call as autocorrelation means, that whatever happens in this year going to impact next year, and next year going to impact the other years, and so on and so on. If you can think that, that's the error term. So the error term of this particular year will affecting the error term of next year, and so on. So that's what's happening, right? So the kind of a simplest, what is the serial correlation scheme? The most simplest one is what we call T minus 1. This is what means that the T minus 1 means that one period of time before. For example, yesterday, we call it T minus 1. Today is called T, and tomorrow is T plus 1, right? And T minus 4 means that 4 period of time previously, 4 days ago, perhaps, if this is daily data. If it talks about annual data, will be 4 years ago, right? So that is a so-called serial correlation or autocorrelation scheme. So we have, if we have this kind of a T minus 4, we call it AR4. If we have T minus 1, we call it AR1. AR is called the short form for autoregressive scheme. Autoregressive, which is very much related to autocorrelation. All right, so we expand the model actually. We will expand the model of estimation in a while. I will show you later. So this is AR2 and this is ARP. Why is AR2? Because this one's supposed to be 2, not 1, right? So you have T minus 1, T minus 2 here, and the ARP, because we do not know the lag, LAG, lag. We do not know the lag, right? We do not know the numbers of lag, so we call it ARP in that sense. So it means that autocorrelation may be dependent on more than one previous observation of the error term. So it can be AR1, AR2, AR3, AR4, AR5, and so on and so on and so on. And it's what we call as autoregressive of order P in that sense. We move to the second part, part 2. What is the consequences of having autocorrelation? What's the consequences means that what will happen if there is autocorrelation inside the regression? Right, you still remember this one will be mostly very much related to BLUE, BLUE, which is best linear unbiased estimator, right? Unbiased estimator, which is very much related to, it must be linear, it must be unbiased, it must be efficient, it must be consistent, right? Basically, that's 4 condition. So, number 1 here, the estimated coefficient are still unbiased. So, unbiased is still there. But the variance are no longer smallest. When the variance are no longer smallest means that the estimated coefficient becoming large. No longer smallest, no longer unique, no longer the most unique and smallest one. Means that you cannot achieve efficiency. They're no longer efficient, right? No longer efficient, which means that they are not blue. But they are unbiased. They're unbiased but not blue, right? What will happen? Then this one will impact the other consequences include will be the residual variance will unlikely underestimate or overestimate. And then it can be the variance it may be underestimate, and then the F and the T might not longer it's no longer valid because of the standard error here, and the variance are either overestimate or underestimate. So you have a problem there. You have a big problem there. Unbiased but not blue, and the result is no longer valid, or in other words, is that it's questionable in that sense. All right. So let us move on with the next slide. How to detect? This is the third part of the slides. How to detect now? So we have few methods to detect autocorrelation. Detect means that it's like right now the most famous one will be the swab. Either you do RTK antigen or you do the PCR to detect the coronavirus, right? To detect the coronavirus. So detecting autocorrelation. Right, that's detecting autocorrelation. You have the informal test, which we're not going to discuss because we're going to discuss the formal one. The formal one, this is the page number. You can refer to Gujarati and Porter textbook that I give you, soft copy. We have Durbin-Watson D-test, we have Durbin-Watson hash test, and we have Bruce-Godfrey. Durbin-Watson D-test is available in eViews. The Bruce-Godfrey LM test is available in eViews, but Durbin-Watson hash test is not available in eViews. This one you have to calculate manually. Right? So what is Durbin-Watson D-test? Let me show you what is this all about. Durbin-Watson D-test is used to determine if there is first-order autocorrelation. So it only can take AR1. This is the condition. All right. So this is the statistic given. Not worry too much about this, although you need to calculate it in some sense. This is the steps or the assumption that you need to meet. The regression model include an intercept. Normally we have intercept. Only first order in first order autocorrelation means that only AR1 here. No missing observation. Regression model does not include a laggard dependent variable as one of the explanatory variable. This one is interesting one, right? No laggard dependent variable means that no y t minus 1. Right? I'll tell you more about this after this. Right? When we do the estimation. Right? And then this one, for example, right? So this is not suitable for this assumption. Here have laggard means that you have extra variable here. If you see this variable, yt minus 1 is actually from yt. So it means that we call that lack of dependent variable. You see this a lot. after this particular chapter. This is something new for you. All right. So the next step is that if the P or the row here, if near to 1, we have what we call as extreme positive autocorrelation. If it's near to 0, means that there's no autocorrelation. If it's extreme, the other side, -1, then you have negative autocorrelation. And the D value, the D calculated value is actually from 0 to 4. Can go from 0 to 4. How to do this? This is the steps. Run the regression, obtain the residual, compute D, find out the DU, DL. DL is D lower and D upper. This one is from the table, the Bin-Watson table. Which is available in the textbook and also certainly available in if you Google it around. For example, like this. If it's 40 observation, 3 explanatory variable, the DL is 1.34, the DU is 1.66, that's 5%. And make conclusion, right? So as I said just now, the value of D is actually from 0 to 4, right? From 0 to 4, and you have this DL, DU. You can always draw this so-called figure or graph to ensure that, to know that your calculated value belongs here, or belongs here, or belongs here. Which column does it belong to? So it's the lower bound and the upper bound, the DU and the DL. All right. So if it's somewhere here, means that no autocorrelation. If it's somewhere here, indecision, this is where these tests are questionable. But if you are here, then means that you are either you have positive autocorrelation or negative autocorrelation. For example, like this, 1.23 is here because it's lower than 1.34. For example, this is the value, right? So I want you to try this. Once you watch this video, you can always try it yourself first before we try it in the class when we talk about this particular chapter pretty much soon. This is actually the answer for this one. And 35 independent variable, 3, the Bin-Watson, this statistic is 1.23. Do we have first order autocorrelation? What is the answer? What's your answer? Yes, it's lower than 1.34, means that we have positive autocorrelation. All right. If it's let's say 1.35, then it's somewhere here indecision. Indecision. Tidak dapat buat keputusan. Indecision. That's the first test. The second one is what we call as the Bin-Hash test. The Bin-Hash, this is the formula. This is the formula. If you see here, the formula includes the D, means that it must have the D, means that the Bin-Watson to calculate it. In the presence of Leggett, if you have Leggett dependent variable, like this model just now, if you have this type of model, then the Bin-Watson is not suitable. So you must use the Bin-Hash, like this one, right? The Bin-Hash like this one, and this is the formula. The N is the sample size, 1 minus N, and the inside this bracket is variance, not variable, variance of coefficient of YT minus 1. All right. For 5% is about this 1.96 because it's follow normal distribution. Again, this is the other example. Steps. The alternative, mostly used in E-views, will be the BG, Bush-Godfrey Lagrange multiplier LM test. Lagrange multiplier is LM test. Right. This will be using for higher order autocorrelation. It doesn't matter what's the AR, AR4, AR5, AR6, you can use this. So this is a much better test. We are, in other words, what we're trying to say that the Bin-Watson is like perhaps like a basic phone, and then the Bin-Hash is an upgraded phone, and then Bush-Godfrey is much more upgraded phone with camera, with 4G, 5G, or whatever G that you have, and all the other functions. So it's a better version of that. So this is the steps, and this is the formula. The formula is pretty much easy. Sorry, this is the chi-square. We use chi-square. So N minus P. P is autocorrelation scheme, right? Where there's AR4, AR5, then you write 5 there. So N is the sample. Let's say 20 minus 5 times the R squared. That's it. That's your calculated Bruce Godfrey, and then you compare with chi-square statistic. For example, like this. This is one example of regression. For example, we have the regression like this. This is the result of the regression. This is the Durbin-Watson, right? The Durbin-Watson here. If P means that the coefficient of autocovariance or autocorrelation scheme or autoregressive error structure is order 3, computes Bruce Godfrey test. How we interpret the BG test, right? A answer is here. This is the A answer. For example, like this n minus p, n is just now given here, n ada n 42, n 42, right? Minus p is 3, and times r square 0.99. This is the r square, right? You get this result 38.961. With degree of freedom you find from the chi-square table, you reject the H now. So it means that there is autocorrelation, right? I want you to do B. Try this before we go in the class. Try this first before we go in the class, and you can share with me your answers when we do this in the class, right? So this is for chapter number 9. So you have 2 things to do. Perhaps let's to check the answer. Just now, this one is already provided the answer, but it's okay. You can always do it again. And this one is to know to calculate the Durbin hash. What's the formula? The formula is here. This is the formula for Durbin hash. Try that on, and we shall discuss it further in the class, for sure. We come to the last part, the remedial. It's like what happened right now. We have the swab test for detecting COVID-19. We have the vaccine to solve the problem, the vaccination to solve the problem, to give certain kinds of medications so that can kill the virus of corona virus here. All right. So that's the remedial. One of the most famous remedial measures for autocorrelation is actually what we call as a Cochrane-Occott iterative procedure. This sounds a little bit. This is one example. I'll give you another example and few more videos actually in the YouTube, which I will share with you in the ellipse to see that there's a few methods actually how to solve this problem. One is what we call as Cochrane-Occott iterative procedure. For example, we get this regression, right? With y and the x. This is the r square, low in that sense. This is the f statistic. This is what we see right now, the Durbin-Watson here. The Durbin-Watson here, if let's say we follow the value just now, 0.4638. 0.46, remember this result, 0.4638. Let me go back to the graph or the figure. Let me go back here. 0.4638 will be somewhere here, right? Surely will be here. So it means that you have positive autocorrelation. Reject the hash null. The hash null is no autocorrelation. So you have positive autocorrelation. So you need to solve the problem. How to solve the problem? This is where this is all came to picture, like this one. Again, you put back to that particular this 5-column kind of table or graph, and then you put your figure there. All right, or you can use this simple formula or a row formula to calculate the row, right? To calculate the row, or you can just use this one. Either way, both way, because we're using this value to transform this regression. We must transform using Cochrane-Occott iterative procedure. As the value of rho is 0.7681, we transform from equation from the equation above, and then we come out with a new variable. Come up with a new variable, so that we get a new variable here. Then we re-estimate this new variable. I have the longer version of this actually. The longer version, I'll show you the longer version. This is the new result. The new result. Right. The new result shows that the Durbin-Watson have improved further. Right. Durbin-Watson is 1.6. 1.698. 1.698, if follow this value just now, it will belong somewhere which is above this one. means that they no autocorrelation. And you calculate the rho, it's actually near zero. Near zero, let us go back here again. This has one indication here. Let me go back here. Yeah, here. This is a very important indication. This is the rho just now, not the P here. This is the rho. If the rho is near to zero, there's no autocorrelation. If the rho is near to 1, you must have positive near to 1. And if it's near to -1, you have negative autocorrelation. Right? So that's how we solve for autocorrelation. And that's the end of this particular slides. But we have not ended yet this session. Let me show you also, particularly this chapter number 9. I have this extra remedial measures. This is more detail of cochlear occult iterative procedure with all the steps. Right, simple one, just 2 pages. You can read through this part because they explain that. So this is one method that be used in the literature, especially to solve the problem. I introduce you with another method, another more straightforward method in a while. Right, let us go through this part. So, as I told you, we are discussing assumption number 5, on no autocorrelation. Right, let us go to eViews. Right, let us go to eViews to do the real thing right now, to do the real deal. Let me go to eView 10, and I put back the data that we have. I'm using the data. Let me use the data of this. Let me try with this this manufacturing data. Yeah, manufacturing, export, and GDP data. Right. Let me rename this thing first. Right. You have total export, TE, and then you have GDP here. Right. No problem. Go through this thing, copy and paste. Again, I repeated this process. We'll do autocorrelation, extra another diagnostic test. Right, new work file, 1970. Let me check the time frame, 1970, 2004. Right, 2004. All right, we click OK. We go quick. We go empty group. We put above here and paste. We have the 3 variables. So what we have done so far, let's say we choose this one as a dependent variable, GDP, manufacturing, and total export, open as a group, or straight away, don't have open as a group, we straight away open as an equation. We estimate this regression, we click OK, you come out like this. The other day we have checked. What we need to check here, is this value. If you see this value here, the Durbin-Watson value, this is something that you need to know. The Durbin-Watson value is 0.79069, which actually, which actually can prove that we have positive autocorrelation. Right, we have positive autocorrelation. It's been proven there, 0.79, which is at the lower bound, and is near to 1 in that sense. Right, we have positive autocorrelation. Okay, this is from Durbin-Watson statistic. Let me show you where is BG. How about BG? How about BGLM test? BGLM test is here. View, go to residual, go to serial correlation LM test. This is BG test. Right, just click OK. If you suggest leg 2, we go leg 2. Just click OK. This is your result, only this part. And we read the F statistic. The F statistic, right, the F's 9.599, and the p-value is 0.000. It's actually 0, which reject the H null at 5% level. Reject H null. We have the problem of autocorrelation. relation. So how we solve it? How to solve? Right? As I told you just now, there's a Cochrane-Occult iterative process. The iterative means that you have to repeat the process. You have to transform the data that you have. You have to introduce a new data set inside there. Right? There's one way of doing it, but I'm showing you a much more straightforward way, much more easier way. One way to solve it, as you can see later in some of my few other videos online, and also this particular video, is that we go back to the estimates here. We go back here. We add a variable. Before that, this is the regression. We add lack of dependent variable. Lack of dependent variable, which is actually GDP -1. We add this variable. Right, we add this variable. Why? This one is actually very much closely related to AR1 actually. AR1 is another style of doing it. But I introduce you this GDP -1, which is lack of GDP period, one period before that. So introduce you a new variable, GDP -1. You can just write like this. EBE will recognize it, no problem. So this will be another new independent variable. Other than these two independent variables, you have manufacturing and total export. You introduce another new one, right? Remember this result, and you click OK. This is the new result, and you see the result here. The Durbin-Watson have gone up to 1.7456. But then again, remember once you introduce introduce the lack of dependent variable, the Durbin-Watson becoming invalid. Means that Durbin-Watson is not suitable. Let's look at these slides again. So remember, we go back to this slide. Very much important in this sense. Here, this particular part. If it's have a lack of dependent variable, means that then normally the D statistic tends to be 2 or 0. The row tends to be 0. There's no autocorrelation. That's the meaning behind. So it's near here. It's proof that no autocorrelation. But we have to prove another one. It seems like we solved the problem. So we have to back the BGLM test. Right, let us check back. Go to this one, go to residual, go to the LM test, click on 2, and this is your result of LM test. Now, the result shows that actually you could not reject the hash null. Means that there is no autocorrelation. No autocorrelation after we include lack of dependent variable. That you have solved the problem. We have solved the issue. We have solved the issue now. Right. So this is one solution. Let's go back. If you still remember, let us go back to normality test, just to extra on normality test. Let's see. We still have a problem of normality. Normality still, JB still a problem. Still an issue there. Right. What else we have learned? We have learned also on stability, which is Ramsey reset. This Ramsey reset from the F test, we still have an issue of reset test, reset issue at 5%. we have all these issues still. Yeah. So we have solved the problem of autocorrelation, but we still have the other two issues here, which is the Jabera and Ramsey reset. Why and how? As I show you here, the data is actually we are using just the linear variable. We forget or we do not use. I do not use actually, or I do not estimate the 5 model and choose the best one, which I told you in the previous session, actually, in the previous video of chapter number 8. We should estimate the 5 model and choose the best model based on the CV method. And from there, you do the diagnostic test. What kind of proper diagnostic test that you need. All right? And finally, I want to show you this part. Finally, I want to show you this part is that, finally, I want to show you this part, which is actually to show you actually what is available in this eViews homepage. This is from eViews homepage. We have all this residual diagnostic. For example, we have you have the serial correlation. This is from the serial correlation, right? Serial correlation LM test. Right, the LM test. This is Bruce Godfrey, how to do the estimation, and you have this Durbin Watson also inside there. All right, certainly you have Durbin Watson also. All right, so to show you what is going on here. Okay, so that is for today. That's for now for this chapter number 9. I'll see you in the our online meeting. So adios, goodbye, take care, ta-ta.